Hi everybody, welcome to SPE Live and today's show, Casing Deformation in Unconventionals. It's great to have you all back. My name is Nils Lowe. It is my great pleasure to be your host today. If you're new to SPE Live, check us out on social media, hashtag SPE Live, or find us on spe.org. SPE Live is made possible by sponsorship from the SPE Foundation. Now, today we are picking up from last week's SPE Live on wellbore surveying and wellbore quality. And today we're talking with George King and Neal Nagel and their observations on casing deformation in unconventionals. The possible causes and consequences specifically, and then the consequences specifically the wellbore re-entry, lost frac and stimulation stages, lost production, compromised well integrity, operational limits, and most importantly, lost asset value. Is this phenomena becoming more frequent? Is it poor operational practices that lie underneath, or is it something unseen? Now, if you missed last week's SPE Live on wellbore surveying and wellbore quality, then you can find that also through social media, hashtag SPE Live, or on LinkedIn, YouTube, and Vimeo, or on spe.org. This today is your opportunity to interact and engage with our experts. Ask these two exceptional experts, George and Neal, questions about casing deformation, geomechanics. This is your chance. So please interact with the chat boxes on social media. Start thinking about what you need to know, what you'd like to ask. If you know colleagues that are not watching at the moment, repost us and tag us on social media and see if you can get your friends to tune in also. So, joining us today, let's meet our guests. Joining us are George King and Neal Nagel. So, George King is industry expert and advisor in well completions, fracturing, production operations, and new technology evaluation. He's enjoying life as an independent consultant, having spent nearly 10 years at Apache as a distinguished engineering advisor in completions and stimulation technology, and earlier 37 years at Amoco and BP, again as technology advisor in completions and production. Neal Nagel, an industry recognized expert in petroleum geomechanics with more than 30 years of industry experience, including teaching and training in petroleum geomechanics. He has taught at New Mexico Tech and Southern Illinois universities. His career, 20 years with ConocoPhillips and over a decade at Oilfield Geomechanics, his own consulting company, working alongside his equally expert wife and partner. Neal's geomechanical expertise includes completions and hydraulic fracturing, unconventionals, wellbore stability, field and laboratory geomechanical evaluations, and 3D numerical modeling. I've had the pleasure and privilege of working with these two gentlemen in my past career, so it's a real pleasure to welcome them to the show today. Neal, George, welcome. So today we are going to be looking at casing deformation in unconventionals. So for everybody's benefit, we're going to divide up today's discussion into three parts. Shortly, we'll start with you, George, and run down on current observations and likely causes of casing deformation. Then we'll move over to you, Neal, to talk about some of the more details around the geomechanics and its impact on casing deformation. And then we'll round off with a more interactive discussion with our audience and audience questions. So audience, to you out there, fingers on buzzers and keyboards, please send in your questions to both George and to Neal. Anything you have to ask about casing deformation, unconventionals, geomechanics, and casing deformation, these are the people you should be asking, because these are indeed the experts. So George, Neal, great to have you here. George, we're going to start off with you. If you don't mind, please give us some of your knowledge on observations around casing deformation, casing collapse, and potential causes.
Okay, well, thank you very much, and good day to everyone. The casing deformation problems that we have seen really increasing in the last several years have been around for a long period of time, and we've seen this before, but when you're in vertical wells and doing one frac, they're a lot less common than in the horizontal multi-well frac area. And this is an issue that really has several causes. We'll look at some of them today, really just introducing what we're saying here. And we'll have opportunities to really advance this later on with some SPE programs as well. We'll talk about those later. But there's many different types of the completion problems that we have. And basically it runs from oval casing deformation, from buckling or side loading, and several causes of that. And then it really looks at hole condition, drilled hole condition. What's left over after drilling? Can you complete in that? And will that casing string actually stay round? And it's very important that it do just that, because we're using plug and perf completion tactics a lot more than we used to. And in fact, this is one of the favorite types of completion methods within the US. So before we get really into all of this, I want to make one statement here, that deformation of the casing does not necessarily mean that it has failed, especially when you're looking at the failure being an environmental leak. We're not talking about that. And most of these deformations are going to be deeper in the well. So we're not worried about that environmental issue right now. A lot of this is from the environmental or geologic induced loads, has a lot to do with the rock fabric. But it also has to do with how you drill the well, how smooth that departure is, whether the wellbore undulates, goes up, goes down, goes sideways, and the dog legs really can be a problem. We can step back and look at even the fracturing part of this. When you start in with cool fracturing fluid, maybe 20 degrees or 70 degrees Fahrenheit, and you're going into a formation that's over 200 Fahrenheit or around 100 C, this has an effect on the pipe in that it is going to contract it a little bit, put it in tension if it's held by cement. And anytime you put a pipe in tension, you're reducing its collapse resistance. And there is a tendency there for this to oval. But the non-uniform loading of stresses within the zone is a major contributor. On the geology side, and Neal is going to get into this more in his formation, but I'll introduce here this concept of the rock fabric and how that moves, creep, the response to, say, stresses that you've put in with fracturing fluids and the pressures and the volumes that we're using. Also bedding planes and layers and the different effects of how those work. Now, I'll leave that for Neal in the geomechanics part of this, and let's talk about drilling for a moment or two. And I'm not trying to run drillers down, but their main metric seems to be drill it in as little time as possible at the lowest cost. We need to add a little caveat to that. We have to be able to run pipe in this, run it cleanly, and get down into areas where we know that we're going to be dog legs. And when we speak of dog legs, a lot of time in the drilling report, it'll say a 7 degree or an 8 degree dog leg. But what that really is that is an average over a stand of drill pipe. And that stand may be a triple and it may be 100 feet long. Well, averaging over that will give you an idea of how much it changes from the starting point to the finish point, but it won't tell you what happens in between. On the screen right now is it's a figure here, and it's a recreation of the actual hole inclination and azimuth changes as this is drilled. And this is during a directional drilling run in a mostly lateral part or in the build area right here. The blue rings are where it is trying to go pretty stressed. The light blue, it's trying to go in a straight line, but the darker blue, you're starting to move out a little bit, and then these red rings are radical changes, probably when something was done to the bent sub, or where it's hit a ledge or a change in the formation and has walked a little bit. And you can see right at the end of that, to the far right hand side, that's a pretty severe change in direction. And that is not going to be easy to get a casing string through that particular part. Now, you may see a 7 to 10 degree claim on the drilling, but in this one, we actually found, and this is from Viking Engineering, who I do some work for, that they found a dog leg in there of almost 35 degrees. That's a huge change. If you run pipe through there, that's going to get into a problem with really side loading. And so those are the things that we need to look at. And how do you get around it? You can either run that gyro or the reading here continuously in the drilling sub, or you can put a gyro or a caliper in the hole afterwards to look at the different changes in this wellbore that we're seeing. Now, directional drilling is a necessity, but small changes to this will produce smoother wellbores, and that's what we're really after. So the other piece that happens here right after the drilling and the pipe is run is, how good was your cement job? And we keep coming back to this, and people will have answers of, oh, it's wonderful, to I don't even see it. Okay, you have a design top of cement in those well designs for a reason, and that is to support the pipe, to protect the pipe from the outside, and to give you good isolation in there. We need to put a lot more work into making sure that we get really good isolation on the cement. So failure to do that, that's going to create some problems later. Now let's switch to a couple of things here that are in the design part of the well, and that's the casing selection and the couplings. Casing, the program spit this out, and we look at it in terms of what is the coupling going to look like, how is it made up, etc. But we don't put a lot of attention in the field, or maybe not enough attention to how these are made up. And you can see here from the Viking study that was done on the modified buttress threads and just a buttress threaded connection, that there are some stress points within this. And if you move this along, you will see different stress loads within this area, and the red areas and sometimes into the gray areas here are the high load parts of that. We recommend that a premium thread be used in couplings. This gets you away from some of the erosion problems that you have with API 8 round or a modified buttress thread. So look carefully at your connections, because that's going to help a lot. Another piece is to look at the stresses in the actual casing wall, or actual walls, and there can be some cracking within that. And advance the slide, if you would, to the next picture. This one is an application problem. It had a lot of stress stored in this coupling, but the coupling itself was made so hard. The yield stress in this is above 145,000, really out of range for the P110 pipe itself. But you get into stress corrosion cracking or stress cracking, and these couplings can fail within hours after being put into the well when it's loaded up. So pick your couplings carefully. On the pipe side of this, one of the things you really want to do is to look at your casing. One thing we found at Viking is that the stress loads and the ovaling can be somewhat controlled by using a thicker wall lower alloy pipe and getting away from a extremely high alloy pipe with that is thin-walled. Thicker pipes, thicker wall pipes have less of a tendency to oval. And just keep that in mind as we go through. Now, from the fracturing part of this, there are several catalysts which actually can accelerate or actually create problems. And a lot of these are highly stressed areas, and the catalyst part is what kicks it off into failure. Cyclic loading, for example. We design well strings with programs, and it looks and it will handle the pressure, it will handle all of the loads, etc. But what we don't think about, and what many of these pipe design programs do not take into account, is if you repeatedly pressure this up and depressure and pressured up and depressure, and I'm talking about cyclic loads of 6,000 psi difference bottom hole pressure now, and you get how many of these in a well? Well, I've seen wells that have as many as 200 fracs in them. So coming up and down that much, number one, you're going to slightly enlarge your pipe every time you come up in the pressure, about 2/100ths of an inch, and then relax it. Well, this is in the elastic range, so the pipe can take a little bit of this, but if you keep doing that in one section or another, you're going to see some fatigue actually happen. Additionally, this pipe expansion will break down your cement bonding. Now, the formation can repair that as it creeps around it in some cases, but in others, this is what you might be seeing is a little bit of leakage between zones. Doesn't hurt if you're in the pay section. If you get up high, then it could be an environmental issue and something we certainly want to avoid. So let's watch these things and put some effort behind it. The big issue here, though, is to get ovality in your pipe by these stresses. Now, this becomes important because you need to get a round frac plug down through this to set it and to drop the ball and be ready for your next frac stage. If the pipe keeps getting pushed in and this non-uniform loading, and this can happen for a variety of reasons, but you're putting a lot of stress in here, and as that pipe ovals, you're eventually going to lose clearance between your frac plug and your casing, and you'll wind up sticking the frac plug maybe 1,000 feet higher or more. I've seen one at 5,000 feet above the last frac stage. That's as far down as they could get the plug. Well, then you're left with really some remedial methods to try to make this right. So all of these things have to be taken into account. And as I say, this has been a developing part of engineering for the last couple of years, and we're making some pretty good headway on it. But there's areas in the world that we're still having some problems. And Permian Basin is one. Other countries, China, Argentina, down to Australia and New Zealand, all have reported some issues with this. So let's keep this in mind. The ranking of the problems is really heavily dependent on well design and the fracturing operations themselves. But most of all, take a look at the rock and be really knowledgeable about what's happening. And with that, I'll turn it over to Neal.
George, thank you. That was awesome. Really, really beautiful summary of observations. Just to sort of quickly summarize your summary, I mean, you were talking about hole quality, directional drilling, cement quality, couplings, stress corrosion cracking being induced and enhancing problems. And then, you know, the consequences of ovaling from all of those impacting the wellbore quality. I just want to quickly just mention a few audience questions coming in here. We can maybe quickly address them. Oliver Barreto on LinkedIn, is there a dogleg degree that we should raise concerns before running the liner? So that was to your earlier figure there. George, any comments around that at this stage, sort of severity of dog legs?
Okay, the severity of dog legs, look in the area that you're drilling, look at your offset wells. Do you have a problem there with the drilling style that you're using and the formations that you're in? If you do, then you can get continuous measurement by putting part of that in the bottom hole assembly of the drill string, or you can run a gyro or a caliper afterwards in sections where, okay, I'm a little question about that, or questioning it, and you'll see drag, you'll see other factors in drilling that you'll be able to see this. And if you know that, take the time, put a string mill down through there, clean that hole up, and that is going to minimize a lot of the problems that you'll have.
Oh, thank you, George. Yeah, and just a reminder to audience, last week's SPE Live was looking at wellbore surveying, so gyros, and some eye-opening information and data came across there in terms of hole quality. Another question I just want to pick us up on from Leopoldo Sierra is casing deformation related to geomechanics or completion practices. So this kind of leads us very neatly into your section here, Neal, on geomechanics. So let's lead away in a way to onto the geomechanics. Neal, George mentioned several potential causes of casing deformation, including geology, rock fabric, and non-uniform annular support loads. Is geomechanics a leading cause? What's your opinion here?
Well, good morning, Niels, and thanks for the question. You know, that was a very exciting opening by SPE. That definitely woke everybody up, right? So, as George alluded to, geomechanics can play a significant role in causing the deformations, as well as obviously other issues with the success of the fracture simulation and stuff like that. I think it's critical, however, you know, that we don't jump to the immediate conclusion that the challenge is mainly or even solely geomechanics related. We've got to look at this thing very systematically. We've got to take out operational issues. George touched on the issue of dog leg severity and how those impact the various issues. So geomechanics is oftentimes a significant issue, but I want to caution people not to jump to the idea that, hey, let's go run off and do a geomechanics study. You know, as a geomechanics consultant, I'd very much love to do the project for you, but as stockholder in many of these companies, I got to tell you, I would much rather we go about this very methodically and make sure if we're going to get to the conclusion that it's geomechanics, we want to have solid evidence before we start really going down that road too far.
Sound advice there, but just for the sake of argument for the moment, if we say geomechanics is a significant contributing factor, how does it cause casing deformation?
Well, as George alluded to, and Asha, I think maybe that first slide, if you would put that up. There we go. First, and George alluded to it, casing deformations have been a challenge to the industry for a very, very long time. When Shell in particular developed the heavy oil reservoirs on Lake Maracaibo down in Venezuela in the 1920s and 30s, they started seeing significant casing deformation issues. With the development of Wilmington over in Long Beach, California, we saw significant casing deformations. Eckafisk and Valhalla in the North Sea in the 1990s was another case. And then obviously there was a whole series of casing deformation issues related with deep water drilling in the Gulf of Mexico. So the issue of casing deformations have been around in the industry for a long time. But the good news side of that is, because it's been around a while, there's been a lot of work looking at it. And when we look at all this data historically, it really comes down to four major issues that have related to deformations. First, we've done something primarily to damage the threads or pull the pipe apart at the threads. Threads tend to be a weak element in the system. So we're seeing issues related to the threads themselves, couplings themselves. And again, following up George's comment, that's the issue of using premium connections, for example. Then from a diagnostic standpoint, we really see sort of three primary forms of damage and failure. One is buckling in the reservoir directly from a compaction type event where we're physically shortening the casing. And then the other two are related to shear, whether it's a localized effect like faults. And this tends to be the greater driver along the lateral itself, or shear-related events with weak bedding planes, whether it's laminations or similar effects. This kind of a weak bedding plane slippage is fairly commonly seen, for example, up in a Montney in the build section. So these are the primary forms that we've seen: pull apart or damage at the threads, and then buckling, and then the two different types of shear events.
All right, thanks, Neal. So you described the sort of the main geomechanical causes there. So I guess the next stage is, as you kind of like the diagnostic piece, is how do we create an image of the casing damage to help determine if the geomechanics is the cause or if it's something else? You know, how do we measure or visualize that casing damage? Do you have sort of some general descriptions around that?
Yeah, so there are some open hole videos that I've seen float around where they see, you know, slippage events and everything else, but those are obviously the rare exception. What we dominantly see, and again, George alluded to this, is after we've experienced a problem, whether it's a stuck frac plug or we can't pass with tools, what ends up happening is we'll run multi-finger calipers, and it is the 40 or 60 arm calipers that give us the type of visualizations that you see on the left here. Is a casing buckling. So this would be typically, say, in a reservoir section that was shortened, and we see this buckling effect. And then on the right side, we see a very, very localized shear in the casing. Both obviously present significant issues with running tools, but more importantly, trying to get, say, frac plugs down into the wellbore.
Okay, perfect. So we've got the image. We can identify where the casing's deformed and potential causes to it, like geomechanical causes, like bedding planes and faults, as you mentioned. So what are some of the tools and techniques that we can use to mitigate the risk of deformation in future wells? So we can say, okay, I'm going to drill wells alongside this one. What precautions do I need to take, for example? Neal?
Sure. Asha, if you would move one slide ahead for us. There you go. So heavy wall pipe, that's one that has been fairly routine. Obviously, there's a cost issue, there's an operational issue, but heavy wall pipe works when you really understand the problem and you realize, hey, the extra stiffness of the pipe and the degree of deformation of the formation is going to be so modest that the heavy wall pipe is really going to hold back that deformation. However, in many cases, the reality is we're trying to hold up almost the entire earth, and even heavy wall pipe will eventually be squeezed shut. Now, in the case of production, in the left side of this slide, the upper part, right above the words heavy wall pipe, you'll see that one of the advantages of heavy wall pipe was you still got production even after the deformation. Of course, for our application, what we're talking about today is not so much how do we still make money from the wellbore after the fact, but how do we make sure we're able to stimulate the well? So even heavy wall pipe, it's going to, in the right circumstances, it might be enough. But in many cases, I think what we end up having to do is our primary tool in the toolbox is going to be either under-reaming. If we know specifically where the problem formations are, we can go in and we can under-ream. Along with the under-reaming, would be some application of something like a foam cement, something that provides the isolation we want with the cement, but at the same time does not direct the loads from the formation onto the casing. And that's one of the issues with foam cement. Can we get a cement in there that does the dual purpose of providing isolation, but does not immediately transfer loads from the formation onto the casing, which is the source of the deformation. And then the other, and this is one, again, if we have the knowledge, is simply avoidance. If we know we have a problem area, can we move around it? If we know we have a fault, for example, can we move the well around the fault so that we don't have to worry about fault slippage? Now, if it's bedding plane failure, in the case, for example, with Montney, no matter where you're drilling, you're going to have to go through that area. So avoidance is not an option. So these are the common tools that we have developed over the years. Some applications, heavy wall pipe, or the corollary, which would be premium connections. Underreaming or avoidance are really our primary options.
Fantastic, Neal. That's really good explanation there. So I picked up on something you said, holding up the earth and the borehole being squeezed shut. So really sort of my next question then to you is, what rock properties do we need to know and how do we characterize them? Obviously that's an important part of this geomechanics equation.
Yeah, that's a tough one because, unfortunately, every situation is going to be a little more unique. If we focus that shear failure is probably the dominant geomechanical driver for the casing deformations, whether it's shear failure along fault or shear failure along bedding planes. The first thing we have to understand is in a isotropic stress field, i.e. all the principal stresses were somehow very close together, there's very little shear in the earth, even if we were to induce slippage along a fault or between bedding planes, right? So if we ever had a situation where the stress environment was benign, the shear failure is sort of comes off the table. So from a geomechanical standpoint, what's driving the shear failure is going to be what are the stress conditions, what are the pressure conditions in the earth, and how are those contributing not only to the casing deformation, but our perturbation to those. So take hydraulic fracturing. With hydraulic fracturing, we have stress shadows. So stress shadows is creating a delta stress change, but we're also driving significant pressure change. And that combination of a stress change and a pressure change is what is leading to the release of the shear stresses along either the bedding plane or the fault. So every situation is a little bit different, but to me it starts with what kind of a stress environment do we have? What's the pressure environment? What are the deltas in both of those that we're going to induce with our completion design? And then go from there. Mechanical properties obviously play a significant role. Geometry plays a role. And then George alluded to the issue of what I call modifiers, particularly the issue of temperature. We're heating up or we're cooling formations, cement, steel. All of these are expanding and contracting at different rates. That drives very local stress changes, which could also be contributing to the casing deformations.
Oh, excellent. Thank you, Neal. We're getting some really good questions coming in from the audience. Audience, please keep those questions coming in, those comments. We will get to them very, very shortly and start debating those. Neal, just another final question maybe. George kind of alluded to this, I think. Is the frequency of these events increasing in unconventionals, for example, or are we just becoming more observant that we've had when we need to adapt our operations to this very low cost environment that we're currently in?
That's one of those where I would say all of the above. Clearly, we're seeing more, but part of that has to be an observational issue, right? Once something we may have overlooked in the past is now something all of a sudden we start looking for, and we start finding things that we had overlooked before. But more importantly, particularly, as our laterals get longer, we're putting more frac stages in the ground. That means we're imparting potentially more stress change, we're imparting more pressure change, and those are the primary drivers. So I think, yes, we're seeing an increase, but we also have to understand that part of it is observational. We're now aware that it's occurring, so we're starting to look for it.
Okay, thank you. Right, let's dive over to some of these audience questions. So fantastic questions. So I'm just going to scroll through some of the questions here. Now, let's start off with a question from YouTube, Valent. It really goes back to what both George and yourself are saying, Neal, about the casing design. We've established a long time ago casing design parameters. Do we need to reconsider these for unconventional operations? Is there a significant change in what we're seeing and the frequency of these kind of casing deformations?
George, you want to touch on that one to start?
Yes, I do. Basically, yes, we do need to take this into account. There's a couple of papers out there that deal with it already. One of them was a URTech paper that I was a co-author on, and two remarkable young engineers with Apache came up with a routine here, or program that actually looked at fatigue from cyclic loading. And they actually found that when they changed the number, or when they actually put numbers in here on the number of cycles they had, that eventually it pushed what was an acceptable load outside of the envelope. The envelope actually shrunk a little bit just due to the fatigue. So I would say yes, that is definitely something we need to look at. And it may not be just in unconventional formations. We're using multi-fractured horizontal wells in conventional applications as well in specific areas. So I think we can leave the word conventional or unconventional out. It's going to happen in multi-fractured deviated wells. This is where you're going to see the most problems, and we do need to change the designs.
Neal, do you want to pick up a little bit on that?
Yeah, and so, and again, George did a great job with his introduction, that the industry was founded primarily with horizontal well, or with vertical wells, right? And so we may have stacked fractures in these vertical wells, but typically we thought of a vertical well with a single fracture. And now, whether we count the stages or count the entire number of clusters, people are hoping to create 200, 300, or 400 separate hydraulic fractures along the lateral. Each of those fractures is changing the stress field. Each of those fractures, if they're close enough together, is creating an additive effect in the stress change. And then all of those entry points are creating a pressure change in the formation. So to the extent that our designs sort of come from the realm of vertical wells with very few fractures, and now we have extensive laterals with hundreds of fractures, yes, the casing design has to account for the differences in the formation response induced by the completion.
Yeah, very interesting, Neal and George. So almost it's like we keep pushing the boundaries until it breaks, and then we have to work out why did it break. So, and talking about sort of pressure cycling and frac zones and frac stimulation. So again, picking up on more audience questions here. So I'm going to go back to Jehun Nayavov on LinkedIn, where they asked how much of deformation is caused by current fracturing practices. Is there something that needs to be addressed? And additionally, Nicholas Kotler on LinkedIn also asked if we're considering refracking, apart from the effects of mentioned by George and also you, Neal, we've got additional corrosion and decreased burst pressure ratings. So Any comments around these, sort of refracking and current fracking practices? George, you want to pick up on that first?
Yeah,
please.
I'll lead off on that one. Basically, looking at the fracturing practices, is it going to happen every time? The stresses will be there, but designed correctly, I think we can handle a lot more in terms of either a destruction of cement or a deformation of the wellbore or the casing itself. But let's look a little bit deeper into this and see if we can figure out why. And the why, and Neal has given you a great introduction to the why from the rock standpoint. If you go a little bit beyond this thing and really start looking at the forces within the pipe, it's that cyclic loading that can really get you into problems. But let's move this into the refracturing realm. When you refracture a well, you're in a well that has had a lot of fractures in it already. It has some erosion, depending on the casing design and the couplings that you've used. It might have erosion in the first 20 or 30 couplings under the wellhead. And in the wellhead itself, it's going to have erosion from slick water and loadings of proppant. Different proppants, different erosion rates. But there are a case or two where a refrac has really created a problem in the well, and we've had some leaks at the surface. In one or two instances, the wellhead has been effectively eroded off the well. So watch the corrosion, the erosion, the loads, the cycling in an older well. I don't care if it's a year old, it's still an older well. It's seen that frac before. Go inspect that well very carefully before you risk a refrac into it.
Oh, very good advice, George. Thank you. Neal, you want to pick up on some more comments there?
So, geomechanically, every formation is going to be a little bit different. We don't see, for example, as many bedding plane slippage type failures along the build section in many of our unconventionals as we do, for example, in the Montney. And that reflects the uniqueness, if you will, of the geomechanical of the stress environment in the Montney as compared to, say, the Permian or the Bakken or whatever. So every case is going to be different. So we want to avoid thinking, hey, everyone's going to have this problem, every formation is going to have this problem, so on and so forth. We need to be aware of it. And this is where, obviously, offset data, paying attention to your first well so you take those learnings for the second well are going to be absolutely critical as we go down the road to fully understand, is it bedding plane slippage, or is it bad couplings? Is it a fault related issue? We've got to capture the uniqueness of every situation to build our understanding before we launch off into solutions. But fundamentally, we're changing the stresses, we're changing the pressures on the other side of the pipe. We're obviously doing that inside the pipe, and George has touched on that quite a bit. Some formations are going to be far more forgiving to those stress changes and pressure changes, and that's going to be the critical issue for us. Which are the sensitive formations and which aren't? Which are the ones that are going to be a problem when we put in 200 stages, and which ones are going to take 200 and not have a hiccup, right? And that's the issue.
Very interesting. And it goes back to, I guess, what George is saying also, or alluding to, better documentation of well operations. And maybe we can touch upon that shortly, is sort of how do we begin to build up this database. George mentioned the Viking database earlier. Just on the question around inducing stress changes in the formation. So a couple of questions from Leopoldo Sierra on LinkedIn. He was asking, cyclic loading is important. Do we need to change the way we do the cyclic loading for formation breakdown? Do we need to do steps in injection rates and that sort of thing? And then he had a couple questions also, scrolling down to that one, fracturing fluids, how are they potentially impacting this situation, particularly around, are we seeing more casing failure today in unconventionals because of the fracturing fluids? But also that's, do we need to change how we cycle pressures? George?
On the cycling of the pressures, one of the things that I've been pushing for a long time, and this is not new, I didn't invent this, it was used since about 1988, somewhere around in there, on the first multi-fractured wells in shale, which were actually drilled in the Marcellus, and it was a DOE project. If you look at that, bring the rate up in steps and avoid shock loading the casing or the formation. Shock loads will create breaks at much lower pressure than gradually stepped up rates will do. So you can create a little bit more stability by simply, if you're going to 100 barrels a minute, come up to 20 barrels a minute, hold it for a minute or two till the pressure comes down, stabilizes, raise your rate again by 20, and it would take you maybe 10 minutes to work your way up to 100 barrels per minute, but the shock loading effect would be at least minimized. There's also some advantages if you're trying to open natural fractures, that if you come up in stages, the natural fractures will open, rather than just this shock load of 0 to 100 barrels a minute. Those fractures might not have time to open before it's sealed off, and the pressures keep them from opening. So that's a factor. On the fracturing fluid side, you're going to get the most erosion and the most leakage hydraulically, maybe down a channel in the cement behind the pipe, etc., but you'll get the most leakage with a slick water fluid. Now, slick water is still the frac fluid of choice in most shales, but if you're really pushing the envelope here with a lot of this slick water and a lot of proppant, especially larger proppant, then you are going to see some erosion increases within the well itself. Putting a little bit of polymer in there will give you a kind of a cushion effect right at the boundaries, and you'll get a little less eddy current problems, etc. So that's a choice that you have to make here. But again, using couplings that don't have that gap in the J section, that is a major thing. And the premium couplings are a good place. If you've got any money to spend it on good couplings.
Some very sage advice there, George. Thank you. Neal, do you want to pick up a bit more on the sort of some of the cyclic loading of the formation?
So, as George touched on very quickly, the dynamic loading is a completely separate environment. How the steel responds, how the cement responds, how the formation responds to a dynamic load is different, and tends to be worse. And so, to the extent that we can step up our rate, we remove that dynamic effect. Right? We're seeing more of a static stress change. The bigger issue, I think, is the pressure effect and where the pressure field is. And so the question, for example, brought in the issue of fluid viscosity. Fluid viscosity, obviously, primarily historically from a hydraulic fracturing perspective, has been a function or been a driver for proppant transport. But viscosity, particularly in unconventionals, also influences how far the pressure field is pushed into the formation. So a slick water will have a much bigger pressure bulb, if you will, around a given frac stage than a crosslink fluid. Crosslink fluid, the pressure field will not be that far off of the fracture, right? So viscosity also is going to affect where the pressure is going, how far out it's going, and then that pressure change is going to impact the geomechanics. So that's where fluid viscosity, for example, could come into this issue of casing deformation. Where does that pressure go? How far out into the formation? And then what's the effect of that increase in pressure? Does it cause a fault to slip? Does it cause bedding to slip? That kind of a thing.
Oh, excellent, Neal. That's really, really informative. And sort of pick up a question leading off from what you've just said. So Ashok Srivastava on LinkedIn asking about, do we have the modeling capabilities to understand these cyclic loads and, the impact on the formation and on the casing strength? Neal, do you want to pick up on that with your expertise?
Do we have this is this is one of my favorite topics. We've got numerical tools. There are always issues with the numerical tools, but we have numerical tools that can really, do with lots of bells and whistles. I think where we are today, more often than not every case, but more often than not, it's not a limitation of the tool, it's a limitation of the data. And do we have, for example, if the issue of cyclic loading on casing, and George is going to be able to better answer this than me, but to evaluate cyclic loading in steel, you've got to do the test. You've got to have the data for a given grade of steel. What does cyclic loading do to its strength, its deformation properties, and stuff like that? So it's not a numerical tool issue. It's the data issue. We have the same issue in the formation from a geomechanics standpoint. I think our tools are more than sufficient at this point, at least. And what we're short on is data.
Perfect, Neal. Perfect. We're getting some more questions around the modeling side and also how much of the rock volume we stimulate. So I'm just going to pick these off here. So Kristen Taliaferro on YouTube. Do localized fracture enhanced volumes increase risk of deformation? And Joseph Shaul on LinkedIn, what about activation of small faults during hydraulic fracturing causing deformation? So to me, those are kind of related. Neal and then George, perhaps, thoughts about this, the rock volume being stimulated causing deformation?
Yeah, so the issue of the stimulated volume is always a difficult one because we have pretty good ideas. If we don't get proppant into the fabric, and most often we don't, then that fabric will tend to close with depletion. So the volume may tend to shrink. But from a geomechanical standpoint, again, the two drivers are what volume of rock have we changed the stress field due to stress shadows, and then what volume has seen a pressure change, right? So if we had a very tight formation, no natural fractures, and we had pretty much of a biplanar fracture, then the pressure field is pretty limited around that fracture itself. On the other hand, if I've got a lot of natural fractures in fabric and I can drive pressure, I can have a pressure field around that, the stimulated volume, if you will, much, much, much larger. And so the impact of both of those comes down to, again, sort of what I said before, the issue of data. How far have we driven pressure into the formation? And if we can get a handle on that, then we can start doing what's that pressure change on a local fault or fracture, right? And then the question sort of came to the issue of seismic data, microseismic data. Well, the microseismic data is being driven by a combination of both the stress change, the total stress change, stress shadows, as well as the pressure field, right? But what the microseismic data is evidence of shear in the formation, shear stresses in the formation that we have released, which is, to the extent we think shear deformation is the primary driver behind casing deformations, that's the first step, right? The fact that we're seeing that shear deformation or microseismic events is we're seeing shear events in the formation. Now, does it go from a micro level to a macro level? That's another question. But when we see those induced seismicity, even though it's small, we know that there's shear stresses that we're releasing in that rock mass. And those could coalesce either along fault or bedding planes to cause a more significant casing deformation problem.
Thanks, Neal. George, you want to pick up some more around this before we go
Sure.
to our next question? Yeah.
Okay. And when you're fracturing and you use a step-up approach, and it was done originally here in this paper by Overby and Yost back in 1988, that they did this stepwise increase in the rate to open up the natural fracture systems, purposely done to do that. And basically, they had enough data to show that it actually worked. All right, step forward here 20 years and look at what happens during the frac job. Watch your net pressure, and this could be a calculated net pressure. And please, for the fracture experts out there, I understand that bottom hole pressure is the royal cards that you want to play with, but sometimes you just have surface pressure and slick water fracturing, and if everything is running consistently, it gives you a reasonable effect of what is going on downhole. But watch the pressure changes at a constant rate. And what you'd really like to see is this pressure at surface gradually increasing or even staying constant if you're continuing to add a lot of proppant into the hydraulic layers that are going down here in the well. So keep this relatively constant if you can, or the rate, and watch the pressure. And if this is just steadily increasing at about, say, 1 to 5 to 8 psi per minute, that frac is probably staying in zone, but you're getting leak off into the natural fracture systems. Now, when you get a change really in the slope here, and it goes to about 15 or 20 psi per minute, in many shales, I've had the experience that if you see that shift in that, how fast the pressure at surface is increasing, that means you've got a screen out somewhere in the wellbore and are pushing back that way. And that should set off some alarms about, are you going to really create a lot of stress in the rock, or can you actually get some annular pressure behind an area just due to leak off and it will come into closing. So this annular pressure, if you can generate it, can give you some oval loads, some oval producing loads on your actual casing. So a lot of things that we can see while the well is being pumped. And for that reason, please stay away from these cookie cutter well designs and frac designs. Watch what's going on, try to interpret, gather the data, and really come up with a better design as you go along. You have to plow learnings back in.
Excellent advice again, George. Thank you. I'm making some notes there on what you were saying. So really it brings me to a very sort of succinct question to the pair of you. Do we know enough about the shales, in this case, the shale properties, to really understand what are we doing in terms of stimulating the rock and how the rock interacts with our operation and deforms the casing? Do we know enough in these vast basin type plays? George is
I don't think you ever know. Yeah, I don't think you ever know enough, because each well is different, as Neal pointed out here. And each shale is different, but every well is different. And from the bottom to the top of these shales, you're going to have some variances in there. And basically, we need to be taking a lot more data than we are. We need good downhole data. We need offset well data. We need to gather as much data as we can and then use data analytics to make some headway on what we're seeing, and couple that with some lab results of people taking pressure and seeing what effect does lateral loading on the pipe have. Where is the elastic range of ovaling? When it's relaxed, it goes back to being round, and when is the plastic range? All of these things, there's been some work done on them. We need a lot more, and as Neal said, we need a lot better data and a lot more data.
Yeah, thanks, George. Neal, with all your experience in sort of geomechanics modeling, what's your thoughts and opinions around how little we know about shale?
Well, you know, the number of hairs in my head, like yours, Neal's, have decreased over the decades, and that's been through painful experience. And George is another generation on top of us, right? When I was a young young man, probably just like you, Niels, hey, we're blowing and going, right? And
Yeah.
now, with age, I would argue that we're probably more cognizant of the fact that, wait a minute, we're in a business to make money, right? It's safety first, it's environment second, but then third, these have to be economic companies, and I think that has driven this whole factory mentality. So that's the opposite side of collecting the data, right? There's a point at which economically you accept a certain defect, right? You say the cost of understanding deformation, casing deformations, is weighed against how much is it going to take to collect the data. So that's a challenge that we face. And one of the things that my wife and I have taught in our geomechanics courses over the years is, if you're going into the Permian Basin, if you're going into the Eagle Ford, and you're going to drill 2,000 wells, right? Collect the data on the first well. Does it make the first well uneconomic? Absolutely. But when you take that data and you use it for the next 1,999 wells, all of a sudden that data gets to be really cheap. And I think it scares people when we say you need more data. But what we're really arguing is, let's be smarter about the fact that you're going to drill 2,000 wells. Collect the right data early on, and then you can depreciate, if you will, that the cost of that data across 2,000 wells. All of a sudden, that data becomes really, really cheap, right? And I think the issue that we face is, many times we're sort of firefighting, right? We're 10 wells in, we're 50 wells in, and all of a sudden we start seeing the problem and go, hey, it would have been nice if we had that data. So yeah. It's not just, hey, let's go throw money at this. It's, let's be smarter. If I'm drilling 2,000 wells, let's figure out early on, what's my basic data set? In my case, it's geomechanics data. What's my basic? What's the stress field? What's my pressure field? What's the mechanical properties? Let's have that up, because I'm going to average that cost across 2,000 wells, and then I'm in a position where, when the issues come up, I can do a better job of evaluating it and solving the problem without having to say, hey, we got to go core a well finally. We got to collect all this stress data, right? It's at that point it's too late. So more data is important, but I think we want more data within our economic structure, which means we need to think about, how do we average that data cost across the thousands of wells that we're going to drill in a given point?
Oh, thanks, Neal. Yeah, and that actually brings up a really good point from Olivier Barreto on LinkedIn earlier, saying there's probably thousands of active producers with deformation. So 2 questions based around Olivier's comments here. One, with unconventionals, are we in too much of a hurry to drill and complete? And it's actually us and poor operational practices that are causing this problem. As Neal was alluding to, we're not collecting enough data and making those investments because we are in a hurry. We're trying to make this cheap. And then to Olivier's point, what are the next steps? Where can people find more information and join the debate around casing deformation? So, Neal, I'll start with you, and then George, maybe.
Well, that's one of the reasons SPE is going to have the Deformation Summit associated with HFTC next year, right? To bring people around the table to talk about this. One of the things that we're not particularly good at within the industry is talking about failures. Nobody wants to talk about how we weren't 100% successful. And as a result, people have been loath to publish it, loath to admit it in public. And so the Casing Deformation Summit that we're going to have is going to be sort of that closed door environment for us to be a little more honest with each other and get some issues out on the table. But one of the challenges, again, for us right now, we tend to be loath to talk about failures, right? We focus on success that drives our stock price and everything else, which is fine. But at some point, it would be good, and in a closed door session, as we're proposing, I think that's the opportunity for people to bring forward their issues, their data, their ideas, without, public repercussions, if you will.
Oh, thank you, Neal. George, you want to pick up on that?
I think Neal's done a great job really outlining what we're trying to do, both with this summit and with the information that we've been gathering, both as individuals and as small teams throughout the industry. I would go first to One Petro, SPE's database, which searches 18, I think, different societies out there. It gives you a lot of good background and information. So start there, go to the internet. There's some good research papers out there. Really pick up, and as Neal has pointed out here, we need a list of the things that we need to know going into the design of the well. And really beyond that, look at the basin. Where in that basin can you operate and you know the most about? You're looking for a lot of hydrocarbons. You're looking for a certain condition of stresses. You're looking for depths and pressures. Get those things lined out and then figure out what data do we need to collect to make sure we design a very effective type completion. That's what we need to start with. And you'll have to start, unfortunately, quite a time or a ways before you start collecting money off the production of these wells. And it's just an expense we have to just go with.
Yeah, no, very, very true, George. Maybe this low-cost environment that we're currently in is going to be the trigger to push all of this and produce better practices, right? And bring us together as an industry again to collaborate around this particular problem. And as you said, the hydraulic fracturing conference coming up next year with the symposium around casing deformation, perfect opportunities for people to really join the debate and begin to constructively move us forward as an industry. I think.
Let me jump in.
Please.
One of the things that we've seen, particularly over the last several months, is the issue of the industry embracing more technology. That technology is going to allow us to continue to prosper in these low-cost environments, and I don't disagree with that. The issue, particularly I think here in casing deformations, is not so much a technology issue as a data issue. Now, of course, the technology comes in if we can develop a new technology to get the data faster, cheaper, whatever. But I think what's facing us, particularly in this specific area of casing deformations, is data. And data, it's simply going to cost money, right? I don't see the magic, I don't see the silver bullet technology issue sitting out there to save us on this one. This one is we've got to knuckle down on it and do the hard work, collect the data.
No, very, very true. But maybe, we have these public accessible databases like Envirus does one for Unconventionals here in the US, where they collect and assimilate public available data. Maybe some of that data, geomechanics data, could begin to be shared and included in these public data sets to actually improve overall industry efficiency. Now, I think we've actually exhausted our audience questions. So first of all, to the audience, thank you very much. You've been fantastic. A lot of really good questions and comments throughout this last hour. So thank you. Neal and George, thank you very much. Amazing conversation and really good discussion. Really sage advice coming across from the pair of you on what to do next in terms of casing deformation and understanding it. So thank you very much for making this such a great show today.
Well, thank you.
Thank you.
And basically, that's a wrap up from us today. So thank you to Asher, our producer. Thank you to the SPE Foundation for sponsoring SPE Live. And see you all around next time. Thank you very much. Join us soon. Thanks, guys.